Now you can hear me? Okay. Maybe I'll take my phone out of my pocket.
Are you ready?
This work? No, you didn't plug anything in. Oh, yeah. Brilliant. I, you can't figure out what a polytrope is yet? Oh, what polytrope you are? I can tell you where you fit. I know. Everything I say is being recorded now.
I have a talking here? Yes, but just...
Hello, hello, hello. Can you hear me? Okay. Hi. I hope you guys are all doing well. It is my pleasure to introduce Dr. Ed Young this afternoon. Ed is a professor at UCLA. He started out, he got his PhD at USC in 1990. He then came here as a fellow to work with Doug Rumble, and then went on to teach at Oxford for a couple years, became an associate professor there, and then the United States called him back, and so he took a job at UCLA and has been there ever since. Ed started out his career as a metamorphic petrologist, then moved on to being an isotope geochemist, a cosmochemist. He studied fluid flow on chondrite parent bodies, fluid flow in metamorphic systems, and finally he's somehow ended up in astrophysics and astronomy, which I think is what he will tell us about today. He has a lot of breadth in his research and a lot of enthusiasm that comes along with that. He's obviously most famous for being my PhD advisor.
That's
right. But no, he has this, he's most famous these days around here for having this brand new mass spectrometer that Doug is always telling us about, called the Panorama, which is a brand new mass spectrometer, the only one of its kind that could do really amazing isotope geochemistry analyses. But that won't be what he's talking about today. So it is my pleasure to introduce Ed.
Is it possible to dim the front a little bit? That'd be great, because I have a lot of black slides. Okay, so I could have, there's a large variety of things I could have talked about on my visit here and not mentioned the big mass spectrometer, and I do a lot of laboratory measurements, but what I thought I would do is give you a piece of synthesis that comes about from a series of papers that myself and my colleagues have been writing about whether or not the origin of the solar system was an exceptional event or not, which is something of a philosophical question, but it's also an important scientific question. So this represents a synthesis of astronomical observations, years and years of measurements of isotopic abundances in meteorites, a little tiny bit of which I've done, but many, many other people have been doing for decades, and just overall thinking about origins of solar systems in general. So as I say, the second part of this title is The Case for an Unexceptional Origin for the Solar System. And I'm going to start with this picture here, which is showing the Carina star-forming region. It's a very large star-forming region in our own galaxy. And it's the kind of place that I'm going to argue that the sun was born in. And I think we can quantify that through the radioisotopes that we've got in our meteorite collections. So the question, this is a field of, I'm going to come back to this picture later, and it's a field about 50 light years across or greater than 15 parsecs across. It's a very large region. It's long-lived. It lasts for a very, very long time with multiple generations of star formation and very massive stars. So we're going to come back to the significance of that. But that's really what we're trying to answer here is where did we come from? And I'm giving you the answer first, which is we think we came from an environment that looks like this. Now I'm going to start, as I always do, with a couple of equations. I'm not going to panic because I'm showing equations. But I want everyone to be on the same page with respect to radioactive decay and what we're actually, what our observables are. And then I'm going to explain how these observables can be interpreted in multiple ways, and as they have been over the decades. So I'm going to start with, I'm going to focus throughout the talk on aluminum-26. Aluminum-26 is a short-lived radionuclide, which has a half-life of about 0.7 million years, or a mean life, which we're going to use throughout this talk, of about 1 million years. And it decays to magnesium-26. And the mean life, if you're not used to thinking about radioisotopes, the mean life is essentially 1 over the decay constant. Or another way to think of it is it's the E-fold time for decay. So as the element is decaying with time, the E-fold time is essentially its mean life. So we're going to see this tau, hopefully in this color. I want to point out that I'm colorblind, so I've tried to keep a color scheme throughout the entire talk, but I'm not always successful. So, but I hope that this always has this color. We're interested in aluminum-26 as a signpost for how the solar system formed. Now, first of all, if it's only has a mean life of 1 million years, how do we know it might have existed in our own solar system? We know it because of years and years of observations about the excess of magnesium-26 that exists in our meteoritical samples. So I'm showing you here, just for those of you that have not thought about it before, this is what we call a 3-isotope plot. This is the magnesium-26-24 ratio and the magnesium-25-24 ratio plotted against one another. Everything that in the black dots here are things, this happens to be data from my own lab, but many, many labs long before me were making these measurements. But these show normal magnesium, terrestrial magnesium, and they lie on a line, which obeys mass fractionation as we understand isotope fractionation. But what you see is a lot of samples with excess magnesium-26. They lie to the right of that line. You see it in particular in cases like feldspars and so forth. They have really huge excesses in magnesium-26. Long story short, that's how we knew that there's aluminum-26, this short-lived radionuclide, in our solar system, because the most primitive materials that we look at show these excesses in its radioactive decay product, magnesium-26. So we know it was there. So one possibility is that that aluminum-26 that we know was there was produced by a supernova. So here I'm showing the Cygnus X region, another star-forming region in Cygnus. And you're looking at what are called YSOs, young stellar objects. These are stars forming and their planetary systems around them forming today, or corrected for light years. And then this is a supernova remnant in the same region. So one possibility is that aluminum-26 was produced by a supernova and found its way into our solar system as it was forming. So this would be an analogy for our own solar system formation. And this, in fact, was the kind of logic that has been applied over the years. So, for example, Cameron and Turan wrote this classic paper, The Supernova Trigger for the Formation of the Solar System, which made everyone think along the lines of, gosh, we've got a chemistry that has been influenced by supernovae, for example, proximal to our solar system. And in fact, these supernovae may have, in fact, triggered the formation of our solar system. So this is a very exciting story, right? We exist because some supernova went off next to some molecular cloud, and that's what I mean by exceptional. This is kind of the exceptional argument for the formation of the solar system. And so lots of papers have been written. This is just to give you a sense of the kinds of things. People talk about supernovae exploding and then these little grains entering into the molecular cloud that eventually collapse to form our own solar system. And this short-lived radionuclide is the telltale sign that this is, in fact, how it happened. But there are other sources of this short-lived radionuclide, other sources of aluminum-26 that we have to consider that might not be as exciting as a source, but equally plausible. So one possible source are AGB stars. So this is an image of an AGB star. An AGB star is one that evolves off of what's called the main sequence on the HR diagram. This is temperature versus luminosity. The sun sits on what's called the main sequence. Eventually, the sun will puff up to a red giant, and if it's a little bit larger than the sun, it'll shrink down and puff up again in what's called the asymptotic giant branch. That's the AGB. So these AGB stars, when they go through this phase, eventually throw off their outer shells, and some of the stuff they throw off is aluminum-26. So it's possible that the aluminum-26 came from, say, an AGB star. It turns out to be unlikely, but that's a possibility. So that's one sort of source. By the way, one of the reasons it's relatively unlikely is that these things, this is mass versus time, and you're just supposed to be able to see the curve here. And because these stars are limited in how large they can be to go through this phase, they take more than 30 million years to billions of years to evolve to eventually throw out their aluminum-26, which makes them not such a great bet. But nonetheless, that is a source of aluminum-26. Another source of aluminum-26 are Wolf-Rayet stars. Wolf-Rayet stars are kind of like the AGB stars in the sense that they're stars that evolve off the main sequence, but they're even larger. Only stars greater than about 25 solar masses can evolve to the Wolf-Rayet phase. And so they puff out, and then they start throwing off material, throwing off a huge amount of material, which are winds. And in those winds are short-lived radionuclides, one of which is aluminum-26. So we have to worry about Wolf-Rayet stars as possible sources of the aluminum-26. So we have supernovae, AGB stars, and Wolf-Rayet stars as sources of aluminum-26. And each of them has a rather different implication for the environment in which the solar system formed. So we'd like to figure out what was the source of our aluminum-26 and other radionuclides, which I'll get to in a second. Okay, so in order to sort this out, I'm going to define a few terms, and I'm going to use those terms throughout the rest of the talk. We need to normalize our radiochemistry for normal chemistry. So for example, we're not going to be able to trace aluminum-26 by itself through chemistry, but we can trace aluminum through the chemistry. So we want to divide the aluminum-26 by the stable isotope of aluminum, which is aluminum-27, to normalize away chemical effects. So I'm going to talk about NR over NS. That's the amount of radioisotope over its stable partner. And so an example would be aluminum-26 over aluminum-27. So it's important to remember that's what I mean by NR over NS. And then I'm going to further normalize NR over NS by the production ratio. The different nuclides that are made in stars are made at different rates, and so you have to normalize for the different rates in order to get at the origin of these things. So we do two normalizations. We normalize for chemistry, and we normalize for production ratio. So here I'm calling alpha here the amount of a radioisotope divided by its stable partner divided by the production ratio of the two. Okay? So decades and decades of work have gone into evaluating the numerator of these alphas through looking at meteorites and their radioisotopes. And then a lot of theoretical work goes into the denominator by predicting what the production ratios in stellar environments are for these different nuclides. So this is just one paper showing from mass 10 all the way up to 200 what the different production rates are for the different nuclides. And so that's what goes into the denominator. Okay? So again, we're normalized for chemistry and production. So when you have that parameter alpha, you can use that to interrogate for all the different radioisotopes for which we have really good data. We can interrogate their sources by normalizing for chemistry and for production ratio. And when you do that, you can break down all the theories for the origin of the radioisotopes in the solar system and therefore origins of the solar system, broadly speaking, into two categories. One category I'm going to call chance encounters between pre-solar materials and nucleosynthesis sources, a variety of sources. So the solar system just happened to be proximal to some source here and some source there, and we can figure out where they all come from. And this has occupied a lot of the field for decades, and it's profitable because we learn a lot about the radionuclides and we learn a lot about the potential sources. A competing model would be what astronomers refer to as self-enrichment in massive star-forming regions with extensive averaging. In other words, an environment that gets enriched with radioisotopes because simply it's a young environment with lots of massive stars. So we have two different models. So really what I'm going to be talking about for the next 30 minutes or so is testing these two models. First, describing these two models, and then testing them, and then seeing which one we all like better, okay, and which one we think is right. The first one represents a sort of, I'll say, relatively low probability event. The second one I'm going to argue is less of a low probability event. But nonetheless, I don't want to tinge I don't want to influence you too much because I think everyone has to decide. Okay, so I'm going to talk about the chance encounters first. And to do that, I have to throw up another couple of equations. I'm just going to walk you through really quickly so you understand that this is very simple, because what I'm really doing is taking decades of work and distilling all of that work down into a set of models that I think encompasses all of that work, using the basic equations that people have used, but sort of tying it all together. So let's start with the age of the galaxy is t, and let's imagine a bunch of events that occur in the galaxy with a beat rate, where the frequency of the event is delta. So for example, if you're standing here in the galaxy, it's thought that the frequency with which you would get hit with supernova debris at any random position would be every 10 million years. Every 10 million years, that's the beat rate for being hit with supernova material. That's what I mean by delta. So we can say that the amount of radioisotope relative to its stable partner is the production ratio. For a single event, it's going to be normalized by the delta T between events divided by the total age of the galaxy. All right? And then if you want to sum up all the events, you make a sum over those events, n events, but you have to take into account radioactive decay. So how do we account for radioactive decay? It's just e to the minus t over tau, which is the mean life. So it's e to the minus t over tau, where in this case t is the number of events times the delta between events. So that's your total time over your tau. So this accounts for radioactive decay. And then we're going to recognize that that's not good enough because there may have been a one-off event that happened right before the solar system formed. Okay? So we add to that, we take that sum, we put it in brackets, and we add one additional event with its own delta t. We'll call that the last event. The last event before the solar system formed. So that's the equation. Now, it turns out that this sum right here is a geometric series. So the equation really distills down to this. It's the alpha term, the radioisotope to its stable partner. It has a production term, and it has a couple of exponentials in there that come about from the geometric series and the decay from the last event. We often call that free decay. So the argument I'm going to make is that this equation actually encompasses all of the chance encounter models that people have written about over the years, and I'll show you what I mean by that. So we can, rewriting that equation, this is what I said is alpha, and when you look at this equation, in principle, all else equal, alpha should only depend on the mean life, since you've normalized everything away. You should see a nice regular relationship between mean life and alpha, the amount of your radioisotope, as long as everything is the same. In other words, if it was one event, for example. If there was one event, the isotope should be differing only by their rate of decay. That's it. Okay? By this model. So let's look about how well that works for the radioisotopes in the solar system. For years, people have been plotting diagrams of mean life against something that looks like alpha. So I'm just showing you three plots here, not that you're going to get much out of these plots, but I want you to recognize that they've been used for years to try to understand the origin of the solar system, and I'm going to try to distill it down into something a little neater. So here I'm showing one of Jerry Wasserberg's plots from 1996. This is Lauders and Cameron looking at a similar kind of relationship, and maybe the most recent incarnation of this sort of thing representing the modern era is by Huss et al. This thing here is alpha. This is the amount of radioisotope normalized by chemistry and by production ratio against mean life. These black dots are the solar system values that we glean from studies of meteorites in detail. And then the curves are various model curves. And I'm not going to go through them here. I'm going to go through them on the next plot to show you in better detail. So these are the data. This is the crux of the talk. So if anyone has any questions about these data or how we get them and so forth, you can ask me now because I want you to understand what we're talking about. But this is mean life. This is that alpha that I was telling you about. And here's all the different radioisotopes. So we have uranium-238, uranium-235, 244 plutonium, samarium-140, iodine-129, 107 palladium, iron-60, manganese-53, calcium-41, chlorine-36, aluminum-26. These are the 12 that we feel confident about, that people have worked on for years, where we really think we know their relative abundances. And what we're trying to understand is what these are telling us about the origin of the solar system. So I've got them grouped, you'll notice, by symbol and color, because I'm about to show you how they group in terms of that model that I was just showing you for chance encounters with different sources. So for example, we can put a curve through the long-lived isotopes like uranium and samarium-146 and iodine-129, relatively long-lived, a single curve through those that corresponds to a beat rate of every 10 million years and a delta T of 100 million years since the last time that happened. So what this means is these are production ratios from supernovae, collapsed supernovae, applied every 10 million years until the last event before the solar system formed was 100 million years. In other words, the reason this curve has the shape that it has is because there was a 100 million year time gap between the last supernova material that hit the stuff that made the solar system and when the solar system formed. Very specific model. You notice it doesn't go through all the radionuclides, it just goes through those that I've labeled group 1. This encompasses a large number of papers and a large amount of research that tries to show that there is a link between some of the radioisotopes and supernova formation, for example, pollution. Okay, so we can continue along these lines. Here's a curve between palladium-107 that goes through palladium-107 and hafnium-182. And this is also supernova production terms. I'm sorry, it's AGB star production terms. Sorry, AGB star production terms. And this is possible because a paper was written recently that showed that AGB stars can produce these two nuclides in the right proportions such that they can be related by a single model. It was actually a paper in Nature that linked these 2 points by a single curve. That's how the sort of importance that people put on trying to link individual isotope systems by a single source. If you can, they get very excited if you can put 2 together, you're happy, right? So they got very excited about putting this curve through these 2 points. Now, you notice it also goes through manganese 53, but manganese 53 is not produced in AGB stars. Manganese 53 is produced by supernovae, so you have to have a separate curve for manganese 53 because that's a supernova product. In that case, again, a beat rate of 10 million years, which is suitable for supernovae, and then a final delta T of 18 million years. And I should add, something I forgot to say with the AGB stars is, if you're standing at some average position in the galaxy, you should expect to encounter AGB material on a beat rate of something like every 50 million years. So 50 million years is a nice delta T, if you like, for AGB star encounters, and 10 million years is a nice beat rate, if you like, for supernova encounters. So those curves make sense in terms of those timings. But manganese 53 has to be on its own curve, so now we have 1, 2, 3 curves. And iron 60 also mainly, in the main, is a supernova product. So iron 60 also has to have its own supernova curve. It can't use the uranium curve because it doesn't fit on the curve. We can't find a fit that makes them all line up. So iron 60 has its own curve, and that's 10 million years with the last event of 10 million years. So that fits quite nicely. That's nice. Looks like that's a good origin for iron 60. Okay, and then we're left with the really short ones. Remember, this is mean life. So these are all things with half-lives less than 1 million years on the left here. How can we explain those? Well, you can put one curve through those that has a delta of 50 million years and a last event of 1.3 million years, with just an expression of the fact that they're short-lived radionuclides and they decay fast. Right? So we've got a model, and this, I think, is an argument that all of the models that have come that have talked about chance encounters can in one way or another sort of be stuffed into these end-member models that explain these 12 radionuclides. So we're talking about trying to understand the solar system in the context of these different events. So we're talking about at least 5 different calculable events that went to produce the radionuclides that we have. And so you might be inclined to suggest that what we're looking at here is we take disorder in the data themselves and then sort of order them according to these events, and that is our chance encounter model. By the way, so here I'm just putting up the chi-squared, the reduced chi-square of 1.14 for the combined fit, but it's not so hard because we're pushing curves through points. Now, my concern with all this is that it smacks a lot of sort of Ptolemy's epicycles, right? You remember the epicycles, and you try to explain, for example, why the planets appeared to reverse in the sky, and you produce all these orbits upon orbits upon orbits. And it seems to me that if you have enough epicycles, you can sort of make any trace across the sky you want. Similarly, if you have enough curves for sources of radionuclides, you could have a curve for every individual radionuclide if you want. But are you really learning anything about the origin of the solar system? And I think my argument is that you may not be. So I worry that this is just too cute. So we have the chance encounters model represented by these 5 curves. And so now what I want to do is explain an alternative, which is a self-enrichment model. Now, to explain the self-enrichment model, I've got to go through a little more astronomy, a little more stellar evolution before we get to looking at the radionuclides again. So bear with me for a few slides so that we're all on the same page. And this is where we've written a series of papers to try to get at this self-enrichment model that starts from what I would say are very disparate areas. That this is not what the individual investigators were setting out to figure out, but we took all these data and put them together, and I think it makes some sense. So the first piece of information that we're going to use is we can look at the galaxy, not we, but the people that do this, and create a map of where aluminum-26 is in the galaxy today. This is a map of aluminum-26 in the galaxy today as traced by 1.8 MeV gamma rays that come from the decay, okay, of aluminum-26. And you see, if you know anything about the galaxy, what you'll notice is that this looks like a map of star-forming regions in the galaxy. So it traces star formation. So Cygnus, big star-forming region. Skocen, big star-forming region. Carina, I showed you an image of it, big star-forming region. even a little smudge in Orion. Okay? Everywhere where there's star formation going on today, that's where the Illum 26 is. Illum 26 is not at high latitude and low latitude off the galactic plane. You're looking at the galaxy edge on here. So it's tracing star formation. So that's the first observation, that Illum 26 is not uniformly distributed throughout the galaxy, but it's only, or for the most part, you find it in star-forming regions. So we had the thought that that's telling us something about the abundance of Illum 26 in star-forming regions rather than in the galaxy as a whole. So the way people have normally looked at how much Illum 26 is in the galaxy, they take the total amount of Illum 26, they divide by the total amount of hydrogen, and then they scale the hydrogen to an amount of aluminum using the sun as a model, and they say, we have excess Illum 26 in our solar system compared to the galaxy as a whole. What's been wrong with that calculation is the Illum 26 is not distributed over the total mass of hydrogen. It's distributed only over the mass of molecular hydrogen, H2. H2 is where stars form, not in the diffuse phase where you have atomic hydrogen. All right? So we can do a calculation using that observation of the mass of Illum 26 in the galaxy today, which is between 1.5 and 2.5 solar masses. We can take the mass of H2 in the galaxy today, and it's 8 times 10 to the 8 solar masses. We can take the mass of rock relative to hydrogen using the solar system as an example, using the sun as an example. So the mass of silicon, magnesium, oxygen that's tied with those, iron and so forth. Add those all up. That's the mass of rock relative to hydrogen. And then the mass of aluminum relative to the mass of rock, we use chondrite meteorites as a model for that. And then we multiply all those numbers together and turn the mass ratio into a number ratio. And we get a ratio of Illum 26 to Illum 27 spread out in all these star-forming regions of between 3 times 10 to minus 5 and 5.6 times 10 to minus 5. The solar value, as deduced by years and years of work on the meteorites, is 5 times 10 to minus 5. So this notion that Illum 26 is in excess in our solar system because a supernova blew up next to us seems to be an error simply because the amount of Illum 26 that we have in our solar system is exactly the amount of Illum 26 that you would expect on average in any solar system born in any star-forming region in the galaxy today. There's a small correction for the amount of Illum 26 that's changed over the last 4.5 billion years, but it's within these errors. So this is the first thing that made us write a paper saying we don't think the amount of Illum 26 is abnormal in our solar system. By the way, I just go through the same calculation. If you take the numbers that apply to Orion itself, that was for the whole galaxy. If you take Orion itself and the mass of Illum 26 in Orion and do the same calculation, you get between 3.9 and 4.7 times 10 to minus 5. Again, 5 times 10 to minus 5. So we look quite normal. Now, the reason we started down this path is because there is a cottage industry of astronomers who love white dwarf stars. And there's a connection between everything I'm talking about and white dwarfs. Because white dwarf stars, if you remember, white dwarfs are the little things left over after stars of moderate size eject all their material, and they become this little thing that's sort of like the size of the Earth, but a fraction of the mass of the sun. And so they have super high gravity. And it's been noticed over the years that some of those white dwarfs have what are called infrared excesses, meaning dust around them. And those dusty white dwarfs have all kinds of heavy elements in them, and you can see this with spectroscopy. You can see the light being absorbed by elements in the photosphere of a white dwarf. Now, it turns out the white dwarf... what did I just do? Oh, cool. It turns out that white dwarfs are so massive that if you put a magnesium atom on the surface of the white dwarf, the gravity is so high it will sink to the core, and it'll sink to the core very rapidly. Depends on the temperature of the white dwarf, but it can be days to years, at the longest, maybe a few hundred years. Okay? So if you see magnesium, silicon, iron, even oxygen on the surface of a white dwarf star, it is not from the star. It was put there recently. And so there's a group of people that study these white dwarfs, and these are, in fact, the best evidence that we have of compositions of rocks outside our solar system. It's in the form of polluted white dwarfs. Okay? So this is a little cover article that was written about this, and this is a sort of an artist depiction. And most recently, for example, we've had a grant to study polluted white dwarfs. And C. Zhu, who is a former graduate student at UCLA, was lead author on a paper where we've just reported the first detection of nitrogen in a polluted white dwarf. And in fact, if you look at the carbon, nitrogen, oxygen, silicon, magnesium, iron, nickel, calcium, this thing is a spitting image for Halley's Comet. And so we actually wrote a paper saying that this is the first extrasolar Kuiper belt object. It's a very nitrogen and carbon-rich body. You're never going to, by the way, you're never going to get a bulk composition of Pluto very easily, right? The way to get a bulk composition of Pluto is to grind it up and spit it into a white dwarf. Then you can see its guts. You can see what it's made of, and this is essentially the experiment that's been done here. So we can do, my role in all this has been as the geochemist talking to the astronomers, we can do geochemistry at the log scale. All this is at the log scale, by the way. And geochemistry is super easy at the log scale because we know everything, right? So geochemists can come along and look at these data and say, hey, that is a geological trend. So let me give you one example of a geochemical trend. There's many amongst white dwarfs. These star symbols are polluted white dwarfs. These circles here are F and G stars. Chondrites would plot in the middle. Solar would plot in the middle. And then these are other reservoirs, geochemical reservoirs represented by Earth and Moon. So mid-ocean ridge basalt, dunite, and then this is 70% core plus mantle here. Now, 70% core, we often see iron-rich objects in the polluted white dwarfs, but we also see iron-poor objects, and they almost always have a trend that looks something like this. And this trend is geochemical, if you think about it. It could have been in any direction, but it's not. It's always in a trend that represents the separation of material in a planet, like we see in our solar system. So, just as a sort of stark example, this is a palisite meteorite. This is the kind of material that we think these star symbols represent in the polluted white dwarfs. And also, this point right here falls right on a mixing curve between mostly core and crust. And in fact, there are meteorites that, I was going to say Psyche is one of these objects too, just for fun. I mean, but there are meteorites that look like a mix between core and crust. They're called mesositerites. So this is one of these sort of things that we find quite exciting, that we're actually doing geochemistry in polluted white dwarfs at the log scale. Okay, so what you're supposed to take away from this is we see mantle, crust, core in extrasolar planetary objects that have hit white dwarfs. All right? Now, it turns out the mass, I'm just showing a calculation here. I'll go through it very quickly, but we can write a simple differential equation that represents the mass accretion to the surface of these white dwarfs. And when you go through the exercise of looking at the mass balance, on average, what you find that the vast majority of the objects that are hitting the white dwarf have the mass of something like Ceres in our own solar system or smaller. They're usually somewhere between Ceres and Vesta-sized, or maybe even slightly smaller. They don't represent, they're not Earths. These are not Earths hitting the white dwarf. We can go through those arguments, but I'm just showing you here an average calculation. So if we take a typical average accretion rate for a population of certain temperature of white dwarfs, we get 1.4 times 10 to the 8 grams per second. We can get that rate. The mean cooling age is 230 million years, and so we can calculate that the mass that accreted over that interval is about 1 Ceres worth of mass. The point I'm making is these are small bodies, and yet these are small bodies that differentiated. They're small bodies that turned into mantle, crust, and core. We see them shredded and then accreted to the star. So it turns out that if you're going to be a small body and you want to differentiate, the only heat source that you have that allows you to differentiate like that is aluminum-26. When you're the size of Ceres, there's not enough potential energy from accretion to heat you up. There's not enough collisional energy to heat you up. The only source you have is aluminum-26. And this is just a diagram to show you this is accretion time versus radius of bodies. And basically there's a cutoff below which you cannot melt. So these are unmelted bodies to the right in the blue colors, and these are melted bodies to the left. And we can go through a simple calculation to show that with a typical formation time of about a 1.5 million years from molecular cloud to the first planetesimals in a planetary system, you can calculate the minimum aluminum-26-27 ratio that you need to melt those bodies, and it's about 6 times 10 to minus 5. Okay? And that'll adjust if you shorten this time or lengthen this time. But it's somewhere in the neighborhood of 5 times 10 to minus 5. That is to say that the polluted white dwarfs, this is not what they were looking for, but the polluted white dwarfs, the fact that they have bodies that have cores and mantles and crusts are telling us that those things had aluminum-26 in them with a complement that's similar to our own solar system. So this is driving us again to think that the short-lived radionuclides in our solar system are not unusual, but they're really typical. Okay? So where might they have come from? Well, one possibility is Wolf-Rayet stars rather than supernovae, as I mentioned before. Turns out that something between 45 and 70% of Lumen-26 in the galaxy could come from Wolf-Rayet stars. This is one of these massive stars. This one is thought to be 70 solar masses before it loses a lot of its mass by winds. And so we start thinking about, and there's a number of people thinking about Wolf-Rayet stars as the source of Lumen-26. It turns out that Wolf-Rayet stars produce Lumen-26. They also produce calcium-41, chlorine-36, a smidge of iron-60, and a smidge of palladium-107, and these other things. So they are sources of different radionuclides that we need to consider. And we have estimates of these abundances from papers like this by Arnold in 1996. So here's the picture. If you are in a star-forming region, in a molecular cloud region that lasts for a long time, kind of like showing here for Carina, you have a couple of sources you can consider. The two sources I'll consider here are supernovae and Wolf-Rayet winds. Wolf-Rayet stars are massive. They live short. They die young. And so they're going to die near the molecular cloud, and they're going to spew their products out into the molecular cloud. They're proximal to the cloud. Supernovae, the vast majority of supernovae are relatively smaller masses, less than 20 solar masses, less than 18 solar masses. Between, say, 10 and 18 solar masses is where most of the supernovae live. And so they're going to, for example, travel a long way before they blow up. So if you take an average interstar, if you like, velocity of 10 kilometers per second, and if you imagine a certain lifetime of these things, in their lifetime, they're going to travel more than 100 parsecs. And this is only 15 parsecs in this massive star-forming region. So the majority of the supernovae will flee the scene before they blow up. This is not the case of the Wolf-Rayet stars. Wolf-Rayet stars will only, their progenitors will last maybe 3 to 5 million years, and then they start shedding their winds. So they will be more proximal. So we contemplate this picture, and then we can write a two-phase equation for a two-phase interstellar medium, one composed of cloud material and one composed of intercloud space. And this is just the mass balance equation. So I want you to look at, this is the alpha I've been talking about. This is the mean life I've been talking about. And there's a couple of other parameters. Tau MC is the lifetime in the cloud, and XMC is how much cloud there is in the galaxy at any one time. These are new model parameters. So expanding that equation, this is just the log expansion of alpha. The abundances, the production ratios, 2 times the log of tau minus this term, which includes the cloud fraction, as I mentioned, and the cloud residence time. And then in addition to the production ratio that normally goes here, we have to consider production from supernovae, but also an extra production from winds that are proximal to the star-forming region. So we have this fit parameter available to us, and we have this fit parameter, which we can constrain in our model. So with regard to the efficiency of winds versus supernovae, one interesting aspect, this is another aspect where you learn things when you talk to people outside your field that you might not have known. There's a controversy about whether the progenitors that produce Wolf-Rayet stars end their life as supernovae. We're always taught that every massive star blows up. But there's some controversy about whether stars greater than, say, 25 or 30 solar masses blow up at all. They may just kind of go, and then implode and form gamma ray bursts. And so there was the, one example of that is the Cygnus X1, which is an X-ray source, and it's essentially a black hole that formed without forming a supernova, because they can tell because it didn't get a supernova kick in its velocity. But there was an argument not long ago that supernova 2013 CU is from a Wolf-Rayet star, but then a paper came out right after that saying, and they can rule out a Wolf-Rayet star as the source of this particular supernova. So we have debates about whether or not Wolf-Rayet stars generally end their life as supernovae, but that would also go towards whether or not the short-lived radionuclides mostly coming from Wolf-Rayet stars are supernovae. So that feeds into one of the model parameters. This model parameter will be low, the efficiency of winds versus supernovae, if every Wolf-Rayet star explodes as a supernova. But it'll be extremely high if Wolf-Rayet stars tend to collapse as black holes and not form supernovae. This is quite apart from the geometric argument that supernovae flee the scene. So that also feeds into this efficiency. So we have a number of things that feed into the efficiency. Okay, and then the time scale if you take the mass of molecular clouds and the star formation rate today, you get an isolation time, a mean isolation time of atoms in molecular cloud material of something like 280 to 840 million years, which is our tau MC. So, this is what they say is the money slide, okay? If you haven't been paying attention, please watch this because this is really cool, okay? This is, we're going to posit, based on everything I just told you, we're going to put forward an ansatz. The ansatz is that 26 aluminum is absolutely normal in our solar system. We can't prove that, but we're going to assume it's true, and we're going to validate or invalidate that assumption based on how well it works for everything else, which is sort of the definition of an ansatz. So here's our data. Here's our data. We're going to put a curve through those data right there that represents an isolation time, average isolation time. If you're a radionuclide, your average time spent, average time, not the actual time of every atom, but average time is 200 million years. Think of this as giving you the flux rate between two boxes, two parts of the interstellar medium, okay? And so we have a curve that looks like this. It explains the longer-lived radioisotopes. We go from uranium down to manganese-53. This reflects that two-box model. You notice this has a shallower slope than the curves you saw before. It goes right through the longer-lived isotopes. Okay, so now we're going to assert that aluminum-26 is not in excess, but really it should be on this curve by virtue of an extra production term due to winds, which were not in the original production term because those are essentially only supernova production terms and don't include the massive winds from multiple Wolf-Rayet stars in the star-forming region. So you're adding to the denominator to push this data point down onto that curve. This is an assumption I will make. So there it goes. Okay, that's fine. That's just an assumption. Now, but I told you that, and this is, in order to get down to that curve, this is the efficiency factor that we need. So we have two fit parameters. Two fit parameters to explain everything in the solar system. Sorry. So we have the isolation time in a molecular cloud and the efficiency factor of winds for short-lived radionuclides relative to supernovae. All right? Now, I told you that not only is aluminum-26 made by these stars, but so is chlorine-36 and calcium-41. So let's look at what happens when I use the same fit parameters. This is not an assumption. Okay? This is just using the same fit parameters that make aluminum-26 work. What happens? Chlorine-36 moves from there down to there. This is not an assumption. This is just putting in the production factors from winds. Now, what happens to calcium-41? Calcium-41 moves from there to there. Okay? Now, what about iron-60? I told you a little bit of iron-60 was made in winds. So iron-60 moves from there to there. And palladium-107, you can't see it move. It moves so little. So now we have this. With the recognition that winds are important and the recognition that we think aluminum-26 is normal because of the white dwarf work, because of looking at the map of aluminum-26 in the galaxy, and making the assertion that we are not unusual in our complement of aluminum-26, all of the radionuclides for which we have really good data, aside from a couple that we think are made by irradiance, these all line up, I would argue, pretty well on a curve. Okay? And that curve says that the average isolation time is 200 million years, and it says that the efficiency factor for winds is very, very high compared to supernovae in a young star-forming region. So that's our model. I'm just giving, this is a pause for effect, so you can be impressed. If you want, I'll go back and show you. They all pop up. See, this is okay. We'll go through that again. Right. Ooh. Right. That's the ooh moment. Okay. So we have these two ways of explaining the radionuclides in the solar system. We have chance encounters, and we have self-enrichment. They both give us nice chi-square fits because we sort of required that to be so. The question is, how can we choose between them? And can we choose between them in any kind of quantitative way? And so this got me interested in a very baby kind of small way, but I think it represents a sort of philosophy of science into the ideas of model selection. So to try to adjudicate between these models, I turned to Bayesian statistics because I went to a meeting in Cambridge and there was exoplanet people, and all exoplanet people talk about is Bayesian statistics. So I thought, all right, I got to go learn some Bayesian statistics. And so I'm applying it not in, a Monte Carlo Markov chain, very fancy normalization thing. I'm just using the basic tenets of Bayesian statistics. The basic tenets are that you're interested in the probability that a hypothesis H is true given the data X. Most of what we do is worry about whether or not the data is true given some hypothesis. But in the end, if you think about it, what you really are after is whether your hypothesis is a high probability hypothesis or not. And the way to get at that is using the tenets of Bayesian statistics. So just the basic model is you have some prior probability that your hypothesis is true. You have a conditional probability that says if that hypothesis is true, our data are either have a high probability or a low probability. And then you normalize that to all the possible hypotheses so that this is just a normalizing factor. And this is usually the problematical thing when you apply Bayesian statistics. And then what you end up with is a posterior probability that your hypothesis is true given the data. That's what we want. But you can make life a lot simpler by comparing two hypotheses and ratioing them to each other and getting rid of the normalization factor. So then this is what's called the Bayes factor. You have the conditional probability, the ratio of conditional probabilities for two hypotheses, H1 and H2. And you have the ratio of their priors before you had the new data. And then you have the ratio of their posterior probabilities. So what I'd like to do is just do a simple little calculation to say what is the probability that the self-enrichment model is correct as opposed to, for example, the chance encounter model is correct. So we can assign a number to it, and then with that number we can start saying, well, okay, maybe we think this is either likely or unlikely. Now it turns out you have to apply essentially Occam's razor in all this as well. It turns out there is a quantitative way to handle that. There's a thing called the Schwartz criterion, which is one sort of information criterion, and I'm not going to bore you through the whole thing here, but long story short, there is a correction for the number of data you have and the number of parameters in the two models that you have. And these information criteria are used in lots of fields, particularly in the health sciences and so forth, to try to correct for the fact that if you had a line through every point, that wouldn't really be much of a fit, right? You'd pay a penalty for that. There has to be a penalty for that, for too many fit parameters. So if we apply this Bayes factor that includes a penalty for the number of factors in each model to the two models we've been discussing, so this is the number of data, in our case 12. This is the number of parameters for hypothesis 1. In one case we have 5 parameters, in the other case we have 2 parameters, okay? And then we have our two hypotheses. And then this is just to remind me to say that we use the chi-squared fits, the probability density for the chi-square fits to get us our conditional. And we put all those things in, and if hypothesis 1 is the close encounters and hypothesis 2 is self-enrichment, plug in the numbers, including the 5 parameters versus the 2 parameters, we get a ratio of 0.017 that Cass and Raftery say is strong evidence, okay, against hypothesis 1 and favors hypothesis 2, which is just a way of saying that we have a simpler model that can explain all 12 radionuclides rather than a more complicated model, and that should be the most probable model. So that favors the latter model that I explained. So the last little bit I'm going to go over here are the implications of this. And one of the implications is we formed in a massive star-forming region. And the reason is there's a thing called an initial mass function. That is the mass function of the masses of stars that form coevally. So the more massive stars are more rare, and it turns out the more stars you have, the more likely it is that you have a massive star. And so the way you can think of that is if I have a bunch of blue balls and an orange ball, if I sample them all, I'm always going to get an orange ball. That's like saying I have a massive star-forming region with lots of stars representing the initial mass function. I'll always get a few big stars. However, if I have small star clusters, so I'm sampling from the initial mass function just little bits at a time, sometimes I won't have a really massive star, and sometimes I will. So the probability of having massive stars goes up when you have larger clusters. So we formed in a region with lots of stars because it looks like we have a telltale signature of Wolf ray pollution of short-lived radionuclides in our solar system when we formed, and it's the same kind of pollution that occurred in other massive star-forming regions that we see today in the galaxy. So that's one implication. Another implication is that we have a normal complement of aluminum-26, as I mentioned, and when you're in a massive star-forming region, this is just a little model I did for time versus the massive aluminum-26, and you see it bounces around, but it bounces around an average. So even though it has a mean life of only 1 million years, it can persist at a kind of average value for many tens to hundreds of millions of years as long as star formation keeps going. So it's a little bit like, for those of you that do isotopes, if you think about secular equilibrium and a really short-lived isotope in a decay chain, it has a finite existence even though it decays really quickly because it's a steady state between production and loss. And then last thing I'll say, the last implication really is that this is, in that model, this is the log of Lum 2627. This is frequency. The gray histogram here is the amount of Lum 26 in different populations of grains produced in a star-forming region. And what you're supposed to take away from this is there are some really hot grains that have a large amount of Lum 26, but the vast majority of the grains have none, virtually none. Okay, 10 to minus 10, 10 to minus 12. This is our complement in our solar system. This is a Gaussian curve. This is a log scale, so this is a Gaussian curve. We have some average value that is an average of really hot grains and grains that have none. So there's no particular significance to the amount of Lum 26 we have other than the fact that there were some massive stars producing really hot grains. By hot, I mean radioactively hot, in the star-forming region. So we formed in a region like this. This region has multiple Wolf-Rayet stars, like WR25 here. There's multiple Wolf-Rayet stars feeding short-lived radionuclides into the interstellar medium. That material ends up in molecular clouds. It has an average lifetime in molecular cloud of a couple 100 million years, but some of the short ones end up in one of your stars, one of the hot grains, but most of the grains are dead, and we get some average. And so we formed in an environment like Carina today, and there's nothing exciting, sadly, about the origin of the solar system. It's quite normal. And that's the end of that talk. Yeah.
I always like models. I'm fond of that, and obviously so my question is, what's the significance of all this
In the data?
Yeah.
Yeah.
What particular when you break down the rules and
Yeah, they overshoot a little bit, yeah. Yeah. No, I think I would argue a couple of things. One is those error bars are meant to take in the errors in the production ratios, which we gave here a factor of 3. You could argue about the size of those error bars for production ratio errors, but we just put in a factor of 3. Why calcium-41 is below? Well, there's 2 reasons. 1, the measurement may not be exactly right. Or 2, we don't know the production ratios perfectly. Or 3, that they're really, the shorter the nuclide, the less likely it is to be averaged. So in one of the papers I wrote about this in EPSL, I actually put error bars around this curve that blow out like this as a function of shorter and shorter time. You would, in fact, expect more scatter down here than you expect up here because of the shorter decay time, because you're averaging hot grains and dead grains, and you've got to get that average just right to be, to get the perfect average. So I would expect that there'd be some real noise down here. But there's also, there's also some, iron 60, for example, right? I'm using the values from Dauphin from Tang and Dauphin, the latest values measured by MCICPMS. We think those are the right values, but there's a group at Hawaii that think it could be a bit higher, which would throw it off the curve. I hope they're wrong. But, and I think they are wrong, and there's technical reasons for that in terms of the mass spectrometry. But if you think about all the things that go into this, there's a lot of theory that goes into these production terms, both supernovae and winds that have to be in the denominators. All the measurements in the meteoritical materials have to be right. So I think the fact that you can get a reduced chi-squared of 0.95 from 12 nuclides from uranium to chlorine-36 is pretty astonishing, actually. And so I'm not terribly worried about this way. Although I'm amused that that's the first thing you pointed out. So the astrophysicists who work on star-forming regions thinks this is dead obvious. And the cosmochemists think this is crazy. And so, this is, so, that's, yeah, right. Oh, ah. Oh. You might have just walked into my extra slide set. Is this possible? Yeah. Wait a minute. Oh, okay. One of my extra slides is I'm taking a lesson from Lyell, right? That you remember, for those of you who are not geologists, right? Um, lessons from Lyell and uniformitarianism. Many appearances which for a long time were regarded as indicating mysterious and extraordinary agency are finally recognized as a necessary result of the laws now governing the material world. That's what I'm appealing to, okay, rather than making up the rules. But anyway, this is my extra slide. So I thought this has implications, testable ideas. One of the testable hypotheses that generate from this is that we should see a closer association between Wolf-Rayet stars and molecular clouds. So first thing I did was to set out and look at the Wolf-Rayet catalog that Mike Shara at the Natural History Museum produces. So I put on X's here. I've put on where the Wolf-Rayet stars are. And then in blue, that's just the CO survey, which essentially traces molecular clouds. And then I also put in the supernova remnant catalog from Green 2009. And I tried to do the statistics on the coincidence of these things, because you're right, this would have implications. The problem is when you're looking at the galactic plane edge on, there's a huge confusion in distance. You don't know the distances very well. So Shara actually gave me a great idea, which is don't use our galaxy, use a face-on spiral galaxy. So I did that. I went to M33. Okay, I tell you, I had a whole slide set for this. And M33 is a face-on spiral galaxy, and it has lots of Wolf-Rayet stars. And there's a catalog of the Wolf-Rayet stars, and there's a catalog of molecular clouds. So I did a two-dimensional KS test for the coincidence of drawing from the population that represents the molecular clouds and drawing from the population that represents the Wolf-Rayet stars. And there's at a 72% significance that these represent the same spatial distribution in 2D. And then I did the same thing for the supernovae and Wolf-Rayet stars, and there's a 27% coincidence two-dimensionally between the Wolf-Rayet stars and the supernovae. Now, if you're an astrophysicist, everything has to be 5 sigma. So this is not really a very impressive test, but it's in the right direction. And so I'm interested in pursuing this further, whether or not we can establish that Wolf-Rayet stars. The problem with it is Wolf-Rayet stars spend, in terms of the actual Wolf-Rayet phase, they're on the order of 1 million years and less. They could be even much less. So they're just winking in and out of existence, and so it's hard to catch them. Less so for supernova remnants. They last longer, so they kind of have an advantage, you know. But exactly, there are predictions. Yeah. 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 There are some error bars in the x-axis. For example, the iron 60 moved closer to that line because recently its mean life was revised, its decay constant was revised. So there are revisions that happen to the decay constants. There's a fellow that was in our group at UCLA recently named Patrick Bonnke, and he actually spent about 6 months, you know Patrick? He looked up all of the uncertainties in the decay constants. And I've tried to build those uncertainties and decay constants in, but they'd be smaller than the symbols I'm using. But the fact that iron 60 moved tells you that the uncertainties that they cite are not the same thing as the actual accuracy error bars, which are kind of hard to assess. But you're right to worry about that as well. Sure, those could revise. Yeah. Why isn't potassium 40 on that? Because we don't, why isn't potassium 40 on that? I have to think about that. There's an excellent reason, but I can't remember. Beryllium, the various beryllium short-lived nuclides are not in there because we think they're made by irradiation. But I can't remember why I've left. I think it must be the production ratios are not known very well. There's a reason for it. It is. I haven't put curium on there, for example, because, yeah, I'm not putting that on. I'm not putting that on there because I think it takes a little while for those values to settle down, and so I don't. Actually, it's not too far from the curve. I've done it mentally, but I haven't actually done the calculation. But I don't think we know the production ratios for potassium-40. I think that's the issue. Connell probably knows better than I do, but you don't know, or Fuad knows. I don't know. But I think that's the issue. You got to have both the measurement. You got to know exactly what that ratio is, and you got to know the production ratios. Again, if we don't know the production ratios, I can't put them on there. So they have to be things we really understand well. Yeah, and that we think we know the average value for. So. Not terribly. I could go back if you wanted me to. I showed a plot. What's important is their ratios are not sensitive. Yeah, not terribly sensitive. That's right. Sure. No, I just use production ratios. Right. So for all the elements other than the shortest lived nuclides, I use average production ratios over an initial mass function, which people, so what you're saying is that uranium and samarium were essentially the initial function were an initial condition for the solar system, that those atoms were around for 200 million years against ending up in a star, and that we are just averaging over 200 million years those materials, okay? And then on top of that, you layer the winds. And I thought what you were asking me was how much the winds are affected. Yeah, but for the winds, you see these curves parallel each other, pretty much, and they do for aluminum 26 as well. So I just chose an intermediate value here. If I chose the values here versus here, it would wiggle things a tiny bit, but not very much because those ratios are the same. Now it would change that lambda over lambda efficiency factor might change from 4,000 to 3,500 or something if I were to do a range of masses. It's kind of hard to average over Wolf-Rayet stars because there's probably 6 or 7 or 10, but not, thousands. So there is some wiggle in this, but the ratios don't change. Yeah. Yeah, we don't. That's right, but mostly what we see in our AGB star dust, and we know that the star-forming region was not flooded with AGB stars. So there's something that we're not understanding about the selection processes for pre-solar grains. My own interpretation would be the AGB star dust we get is the really old dust that was sitting around in the molecular cloud and just happened to get swept up, and it was in resistant material that just happened not to be homogenized by destroying it and reforming it and destroying it and reforming it in the disk. Yeah. 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 I agree. Yeah. Right. Yeah, so there's some complexity there. There's depending on the temperature of the star, their sink rate is a function of that temperature, and also the mass of the star because of the gravity. So there's this guy, Patrick Dufour, up in Canada who models the white dwarf stars, models those sink rates. There are two models that you have. There's actually three models you can think of when you see a polluted white dwarf. One is that you're in steady state and that there's a continuous flux. Another model is that you're in the sinking phase, where things are beginning to sink. And in the third model is you're just seeing the uptake. If you're in the steady state, you don't have to worry about the different sink rates of the different elements. Most of the elements are the same, but if you go between, say, oxygen and iron, there can be up to a factor of 2 or 3 difference in the sinking rate. So if you're in the phase where everything's starting to sink and you're not in steady state anymore, you have to correct everything for those variable sink rates. But since everything I showed you is on a log plot, that factor of 2 to 3 isn't such a big deal. But that is an uncertainty, knowing which phase you're in. Very recently, last year, in the latter part of the year, they reported the first observation of watching a polluted white dwarf being polluted. They can see the material, the occultation of the material as it's going around and sort of puffing up and hitting the white dwarf. So they now have observations that actually document the stuff falling onto the white dwarf. So in that case, that's a white dwarf that's either in steady state or it's in the buildup. I'm not sure that that's an assumption built in. All you can say is you're seeing an average of whatever that material is. It could be 3 planetesimals. It could be 1 big planetesimal. It could be a collection of comets. I don't think that's really built in. It's just that every time you see element ratios in these polluted white dwarfs, they follow geochemical trends. So whatever the material is, it's been processed geochemically.